All right, ladies and gentlemen. So if you understood the last video, right, we left off really talking about the rules that we did for how to analyze basic circuits, okay? And we generated a bunch of equations with those, okay? And we did one case where we had the current given to us, and we did another case where we assumed the current, okay? But we didn't solve for anything yet. All we did was set up all the equations that we had practiced, figuring out where loops are, how to draw them, et cetera, et cetera. So today I want to solve some problems that mirror what we did last time, but show you what you would typically be asked, how to then generate each one of those equations, and then use those equations to solve for the unknowns that you may or may not have in a given system, okay? So let's jump right to it. Okay, so here is the simple circuit that I want to solve, and it's going to look very similar to the one that we did in last class. I think here I'm just adding an extra resistor, okay? All the values of the resistors are given: 2 ohms, 3 ohms, 4 ohms, 7 ohms. 2 batteries are attached to this, a voltage 1 and a voltage 2, and they're connected such that this is the way the wires line them up, okay? What I want to find is the total current. There's only one current, one and only one current here because there's no junction, right? That should be the first, that should make perfect sense. And then I also want to talk about, well, what's the potential difference between A and B? No problem for us to do that, right? Because we know the potential difference around any closed loop is 0. From A to B is not a closed loop, right? Just from here to here or from here to here. And either way we get there, again, we're just going to use Ohm's law to figure out the net potential that we get there, okay? So I want to do this using the stuff that we discussed in the previous video. Pause, and then I want to do it again, showing you that all the stuff that we learned previously about resistors and series and parallel can all be applied, and you could still do it that way if you didn't like the stuff that we do here, because all this physics has to be the same. Posted down here, I remind you from the last video, are our standards, right? Okay, we pick in purple, we pick a direction for us to evaluate things. We pick a starting place, which has to be the same as our ending place, okay? And then if we're going with the current, that's how we generate a positive or negative value for the resistors. If we're going across the terminals in the regular way for a battery, we pick up V. Against it, we lose V. Okay, so the first thing that we notice, if we want I total here, they did not give us a direction of the current. So we're going to assume the direction of the current. Let's do it one way and then do it the other way and see how the results combine and see if it matches what I told you in the previous video. Okay. All right, I like to always start from the top, okay? And so if I'm looking for how would the current be flowing, okay? Well, I think that the way that it would most likely be flowing, the way that I see it, right, is this battery, E1 is a 12-volt battery, so the current is probably flowing out of it this way, which means it flows here, flows here, flows here, flows here, flows here. Maybe I'm right, maybe I'm wrong. But it doesn't matter, right? We assume the direction of the current. Then we pick a starting place and we pick a direction to evaluate. I'm going to pick this as my starting place because I told you in the last video, I like to start from the top left, and the direction that I like to go is counterclockwise, which is convenient for me here because I'm going in the direction then of the current. No junction, which means that I'm just going to call I total the same as I, because wherever one charge has got to go, it's got to go through the others. Here we go. Starting from that top left corner, I go across the resistor R2 in the direction of current. So I lose an I R2. I then go across the R3 resistor in the direction of current. I lose an I R3. I'm now going from the positive terminal to the negative terminal of a battery. I lose E2. I then go in across R4 in the direction of current, so I lose that, but then I come back and I pick up my E1, but I once again lose IR1, and I'm back to where I started. And I generated this equation, albeit lengthy, but it's an equation nonetheless. Put a check mark next to everything I know, underline everything I don't, because now we're actually going to solve this, yes? Don't, I know, don't, no, no, don't, no, no, don't, no. Yeah, there's a lot of underlines there, ladies and gentlemen, but it's the same underline. It's just I. This is one equation, one unknown. This now we can solve for I. How are we going to do it? We gather all the terms with the i's in it and factor it out. If we factor out an I from the first term, we're left with a negative R2. Second term, negative R3. Last term, I'm sorry, fourth term, negative R, oops, R4, negative R1. Only other terms that we haven't accounted for is minus E2 plus E1 is still equal to 0. So let's move E1 and E2 to the other side. Okay. And now we have numbers for each one of these. Okay. So at the end of the day, I is going to be E2 minus E1 over, I'm just going to factor out a negative sign out of all those R1s, R2s, R3s, and R4s. You know what? I don't want to confuse anybody in the video, so let's just leave it. Okay. Getting values for these. 4 volts minus 12 volts on the numerator. And then in the denominator, I have a minus 2, minus 3, minus 4, minus 7. So putting all that together, I have in the numerator 4 volts minus 12 volts is also known as negative 8 volts. In the denominator, we have negative 5, negative 9, negative 16 ohms. Negative divided by negative gives us positive 0.5 amps. And we have our current. It came out to be positive. What does the positive value mean? In the last video, we explained that that means that the direction that we assumed was correct. So the current is actually flowing in that direction. Pause though. What if you just said, I don't believe you, James. I wanted to do it the other way, okay? What if instead of, and it would take me too long to go back and erase all those red marks, what if instead the current we assumed was going in the green direction? What equation would we have then generated? Now, in the last video, I showed you that if we pick a different starting point and we go clockwise or counterclockwise, we're going to get the same result. So I don't need to convince you of that again. Right now, I'm going to say, since we assumed the current in this one, what if we assume the current went a different way? Do we generate the same result? Or if not, how does it compare to the other one? And remember, we said that the magnitudes are going to have to match. So ignore those red tick marks then on this circuit. We're going to assume the current, if we're starting from the top left, is flowing to the right, those arrows in green. Again, though, I get to choose which way I want to analyze the circuit. I always like to start from the top left and go counterclockwise. So I'm going to do that once again. Okay, I'm going to zoom out. That way I can do it up here. So I'm going to do all that now in green to symbolize that it's for the green tick mark. So starting from the top left and going down, I am now flowing against the current across the resistor R2. So I get a positive I R2. Then I'm flowing against the 4 ohm resistor. So again, I pick up a positive I R3. Then green would be to the left, yes. Then green, though, is going from negative terminal to positive terminal, right? Again, if I pencil in the green over here, right, it would be flowing from negative to positive. I would pick up the positive value of E2. Then I would pick up a positive I R4. However, then again, green has to be going this way. I'm now analyzing it again from, I'm analyzing it the opposite way. So I'm going to lose this time the E1. And last but not least, I am gaining because I'm going backwards against R1. Oops, and that should just be an I. R1, and we're back to where we started, and that whole thing is going to be equal to 0. Let me just double check that because, gosh, I should have just went back and erased the red because it's way harder to look at this with both. Green, yes, green is pointing to the right, so I flow from the positive terminal to the negative terminal, so I lose the E1. Okay, so again, we put a check mark next to what we know, underline what we don't. We see the only unknown here is I. We do the same procedure. We factor out I and solve for the rest. So I'm going to go through that a bit quicker than I did in red. Okay, so factoring out I, I'm left with R1 plus R2 plus R3 plus R4 minus E1 plus E2 is equal to 0. So now I see that I is going to be E1 minus E2 over R1 plus R2 plus R3 plus R4. Plugging in our values, this is 12 volts minus our, oh gosh. Nope, I lied. I can't copy my work. Let's pause right here. If we go back, here's where I miscopied, right? E2 is positive, E1 is negative. I miscopied it right here. Okay, now it's copied properly, which means that when I move things to the other side, it is E1, which is positive, minus E2, which is negative. Okay, 12 volts. Let me just make sure that I can scroll back up here. Apologies, we had a little bit of technical difficulty there. I'm going back to my iPad now. Nonetheless, we corrected the error that we had a second ago, but what we see is that we're going to end up, once again, after doing the algebra, with a 0.5 amp current. Now, you might say, well, here we are, right? The magnitudes are definitely the same, but why didn't I get a negative sign if we know the current was supposed to be going in the other direction? Well, there's no junctions here, right? So it's really hard for us to figure that out. So let's come back to that, okay? So let's dive into, I promised you that I would do this another way before we parted ways, okay? These 4 resistors are 4 resistors in series, right? So if there are 4 resistors in series, we can figure out what the total resistance of this circuit is, right? Our total is just going to be R1 plus R2 plus R3 plus R4, right? Which again is R2 plus 3 plus 4 plus 7, right? Is what we said earlier was 16 ohms. Our V total, right? Our V total is going to be our 12 volts, but now the 2 batteries are opposing one another, right? The 2 batteries are opposing one another. One is connected with its terminals one way, one is connected its terminals the other way. So either way, they have to differ, right? So it's 12 volts minus 4 volts, which again is going to be our 8 volts. And so we know that if V is equal to IR for any place in the system, Mr. Ohm sets those laws, then we see that I total, another way of solving this could have just been V total over R total, which would have once again gave us the 0.5 amps. That's using the stuff that we did from last couple of videos instead of jumping into all this stuff. Okay, very good. Let's go into one that is slightly more complicated because it actually has some parallel elements into it, okay? And again, they don't tell us the direction of the current. So just like we did in the last video, I'm going to assume a direction of the current and from there, see if I can find the unknown currents. Now, when I say that I want us to find the unknown I in each element, how many currents are there really, right? Well, there's definitely a current in the left branch. That then, again, let's put names on these, right? That current I1 flows into A and it's going to split, right? Or be combined depending on how we want to say it, right? Again, keeping consistent, I want to say that there's a current on the right branch, I2, right? Which again then flows into A. And so what will have to flow out, I3, such that I1 plus I2 would have to equal I3, because whatever flows into a junction has to flow out. We don't know if those are the proper directions, but that's what I'm going to assume for this problem, okay? So if that's the case, again, just like what we learned in the previous video, how many loops do we see? We see 3 loops, the left loop, the right loop, and the large outer loop. From each one of those, we want to get enough information to solve for I1, I2, and I3. Or if we had I1 and I2, since I1 plus I2 is equal to I3, that would also give us what we need. So let's do it. Let's just do all 3 loops and see which ones we need in order to solve for what we actually want. Okay, so doing the left loop, which again, just like the previous video, says that I will start up in this corner and work my way around a closed loop. So first thing I do is I go from that top left to point A, nothing happens. Then from going from A to B, I flow across, right? And I should have reminded you, right, that I'm doing this clockwise, right? Okay. If I'm going from the top left to A, then from A down to B, I'm going in the direction of the assumed current I3, and I'm losing R1. Then I come back up here, which means that I1 must now be flowing this way, so I pick up E1, and that's got to be equal to 0. We can't ask for anything simpler than that, okay? But before we start solving anything, let's just finish off the job of the other 2 loops. The loop to the right, again, starting from point A and going down to point B, because once again, I'm going to, or I guess, let me keep consistent here. If I'm going to go in this direction, okay, then what am I going to do? I'm starting from A, and then I'm going to the top right. Nothing happens. I go down, then I'm going against the current. So I pick up a positive, what I called I to R2. I go against the battery from positive side to negative side, so I lose an E2. Then I get down to point B, and get from point B to back to point A, I'm going against the grain of I3 times R1, and that's equal to 0. Last but not least, we got the outer loop. And the outer loop, I'm going to zoom out here, again, starting from the top left and going to the right in this direction. The first thing that I encounter is R2, and I'm analyzing against the assumed current I2, R2. I am going against the battery E2, but then I'm going with the battery E1, and I'm back home. So those are our 3 equations, which are going to be more than enough to find our 3 unknowns. What does the first equation buy us? If we put a check mark next to what we know and underline what we don't, the first equation buys us I3 as the unknown. So let's solve it for R3. I'm sorry, I3. Solving it for I3 says that negative I3 R1 is equal to negative E1. Another way of saying that is I3 is equal to E1 over R1. E1 here is the first battery, 10 volts. R1 is the first resistor, 30. So this is 1/3 of an amp. Okay, we keep going to the right, or the one on the right. That one has both I2 and I3 in it. So let's pause on that one, because what if we jump down to the last one? The only unknown there is I2. So we can solve that for I2. Okay, solving that for I2, another way of saying that is I2 R2 is equal to E2 minus E1. I brought the E2 and the E1 to the other side. So I2 is E2 minus E1, whole thing over R2. And I have to go back up to my numbers here. E2 is 5, E1 is 10. So this is a negative 5 in total over R2, which is 20. And so this is a negative 1/4. Okay, again, negative sign here means that we know the value is 1/4, but that current should have actually been flowing the other way. Last but not least, what do we see? We know that the junction rule has to be true, okay, but now we have a value for I2, we have a value for I3, and let's go back and plug that into the second one. If we plug that into the second one, then what we see is if we solve that, oh, I'm sorry. The second one does not have I2, I1 in it. We have I2 and we have I3, so this one is basically just redundant for us, okay? But if we go back to the junction rule, then what we see is that I1 plus I2 is I3. Well, let's make sure that we're all okay with that, right? We said that the direction of I2 should have actually been shifted, right? Namely, what it should have read was that I1 is equal to I2 plus I3, okay? Or another way of saying this is, well, it's basically saying the same thing that we had before. Let's just see what this gives us, right? I2, we said was going to be a positive 1/4. I3 is 1/3. Get a common denominator here, okay, which is going to be 12. So this is 4/12 plus 3/12, which is 7/12 in total current, okay? Or I'm sorry, 7/12 as I1 for the current. Now, that was us changing around our initial assumption of the junction. How did we do it originally in green? We said that I1 plus I2 was equal to I3. Well, let's just say that we continue to roll with that, right? I1 is what we didn't know. So I1 is I3 minus I2. Okay, notice that looks different from the formula that we have up there, right? But if I3 was 1/3, and then we plugged in the fact that we solved this because we incorrectly assumed that that was the way that the current went. If we plugged in a minus 1/4, a minus minus becomes a positive, and we get 1/3 plus 1/4, which again would have gave us the same result numerically for I1, even if we didn't go back in red and redo the actual junction rule. Meaning that we could have just rolled with the fact that we knew we were wrong and we plugged it in instead of going back in. If we wanted to do it and go back and make sure that we did it the right way, we got one answer. If we said that, well, we acknowledge that the current wasn't in the right direction, but we just give it the value that we found, it still comes out to be the same thing. Either way, as long as we're being consistent, these things have to work out. I don't want to inundate you with any more problems. I want you to focus on these two. If you can do these two, you really can do any one of them in the future. So please make sure that before we jump into the next video, which is going to just have more and more of these problems, that you're really comfortable with this one, and more in particular, setting up the equations from the last one. Until then, ladies and gentlemen, as always, if there's any questions, comments, complaints, or concerns, please don't hesitate to ask, and I hope you have a fantastic weekend.